you're welcome back to this channel. I am the complex analyzer, and in this video we're going to talk about even and odd functions. Even and odd functions. Okay, let us talk about even and odd functions, what they are. So let's start with even functions. What is the condition for evenness of a function? A function f of x is said to be even if f of x is equal to f of minus x, or if f of minus x is equal to f of x. So this is the condition for evenness of a function. But for an odd function, a function is said to be odd. The function is said to be odd if minus f of x is equal to what? F of minus x. Or you can say f of minus x equal to minus f of x. It's the same thing. Here we can say f of minus x equal to f of x. Alright? So this is the condition for evenness of a function, and this is the condition for what? Oddness of a function. Let us consider some functions now and see whether they are even or not. For example, f of x equal to what? S squared. This function is actually an even function because if I take f of minus x, what will it be? It is minus s all squared, which is equal to s squared. So in this case now, f of x equal to what? F of minus x, which means that s squared is what? Even. Alright, look at another one. F of x equal to s to the third. This function is odd because if I take f of minus x, which is equal to minus x all to the third, I will obtain minus s cubed. Yes, if you raise a negative number to an odd power, the negative sign will remain. Okay? So from this principle, f of minus x is minus s cubed, and it is equal to what? Minus f of x. That is, if I multiply f of x now by minus 1, I will obtain minus s cubed. So minus f of x is minus s cubed. Multiply this one by minus 1. And f of minus x is what? Minus s cubed. So they are the same. It means that the function is odd. Alright, keep watching. Remember to subscribe and like, share this video to your friends and to your classmates as well. Look at this function, f of x equal to sine x. Sine x is an odd function. F of minus x is sine minus x. And what is sine minus x? Trigonometry says that sine minus x is equal to minus sine x. Okay, so f of minus x is minus sine x. What will now be minus f of x? Multiply this one by minus 1 to give you minus sine x. So we can see that minus f of x and f of minus x, they are the same. So the function is an odd function. What if we consider the cosine? That is f of x equal to cos x. Alright, we said that this function is what? Odd. So f of minus x is cos minus x. Okay, replace the x with minus x. So trigonometry says that cos minus x is equal to cos s. So what can we see now? F of x is cos s. F of x equal to cos x. And f of minus x is equal to cos s as well, which is equal to f of minus s, which is also cos s. So based on the principle of evenness, f of x is equal to what? F of minus x. They are the same. So cos s is an even function. Alright, we can also determine the evenness or oddness of a polynomial function. For example, what number are we now? I think this should be number 5. We are considering f of x equal to x to the 4th plus 3s squared. Okay, this function is actually an even function. Let's see. What is f of minus x? F of minus x is equal to, in place of x, I'm writing minus x. Minus s to the 4th plus 3 times minus x to the 2nd. Minus x to the 4th is s to the 4th. Take note, if you raise a negative number to a power that is even, the negative sign will disappear. Okay? Plus minus s squared is 3s squared. 3s squared. So what can you see? F of x equal to this, f of minus s equal to this. They are the same based on the principle of evenness of a function. So we can say that this function is actually what? Even. Alright? Now, consider this now. F of x equal to, okay, let's say this. F of x equal to 2. 2, is it even or odd? Actually, it's an even function. That's interesting to know. The reason is because I can actually write 2 as 2x raised to the power 0, since we are dealing with a function of x. Okay, so f of x is equal to what? 2x raised to the power 0, which is equal to 2. F of minus x will now be 2 in bracket minus 2 raised to the power 0. Am I right? Yes. In place of the x now, I'm writing minus 2. Minus 2 raised to the power 0 itself is 1. 1 times 2 is 2, which is the same as saying 2x raised to the power 0. So f of x equal to 2, f of minus x equal to 2. Based on this, the function is what? Even. So take note, all constant functions are even functions. Take note of that. Okay, consider the function f of x equal to 3s cubed plus x. This function now, is it even or is it odd? What is f of minus x? In place of x now, let's write minus x. So that will be 3 into minus s cubed plus minus x. Okay, minus s cubed is minus s cubed. That is, we have minus 3s cubed. Okay, plus minus is a minus, minus x. This is f of x, 3s cubed plus s. So it means that minus f of x is obtained by multiplying through by minus 1. That will be what? Minus 3s cubed minus s. So you can see that f of minus x is the same as minus f of x. That shows that the function is odd. So this function is an odd function. So take note now, if we are having odd powers of x in the polynomial, the function is odd. But if we are having even powers, the function is even. So just as we have even functions, odd functions, there are also some functions that are neither even nor odd. Take for example, f of x equal to 3x squared plus 2x. This function is neither even nor odd. Let's check. What's f of minus x? In place of x, I'll put minus x. That will be 3 into minus s squared plus 2 into minus x. So we have minus s squared is s squared. That's plus s squared. Times 3. That's 3s squared. And what will this give us? Minus 2x. So minus f of x, from here now, let's multiply this by minus. We'll have minus 3s squared minus 2x. So you can see that for evenness, f of x is equal to f of minus x. But f of x here is not equal to this, which is f of minus x. So it is not even. For oddness, f of minus x is equal to minus f of x. Okay? But f of minus x here, which is this, is not equal to minus f of x, which is this. So the function does not satisfy evenness and oddness. So it is neither even nor odd. The point is that the function is having even and odd powers. So if a function has in combination even and odd powers, the function is actually a function that is neither even nor odd. That is the point. There are some other things we should know about even and odd functions. For even functions, let's talk more about it. The graph of an even function is symmetrical about the y-axis. The graph is symmetrical about the y-axis. That is, for any point on the graph x comma f of x, there exists a corresponding point on the same graph. Corresponding point minus x comma f of x. That is the point. So the first thing is that the graph of an even function is symmetrical about the y-axis. What does that mean? What it means is that, let me describe it this way, symmetrical. Let's take, for example, the graph of y equal to x squared, y equal to s squared. This is how the graph looks like. Just a rough sketch. Okay, this is the graph of y equal to x squared. I'm trying to explain what symmetrical about the y-axis means now. Let's say this is the point minus a, this is the origin, and this is the point a. If I tend to close this graph now about the y-axis, this is the y-axis, and this is the what? X-axis. The distance from here to here is equal to distance from here to here. Okay, so if I decide to close it up, you will see that the graph will overlap perfectly. Yes, because they are the same. So if I tend to fold it up, it will cover up. That is the idea of symmetrical about the y-axis. So that is one way to identify an even function graphically. If you notice, it looks like if these two sides are the same, if it's a perfect graph, this right hand side tends to mirror this other side, or this left hand side tends to mirror the right hand side. So they are like, the sides are equal, they look alike. That's what we mean by symmetrical about the y-axis. So let us look at the graph of cos x. Cos x is an even function. We just showed that earlier. Okay, the graph of y equal to cos s, y equal to cos x. Okay, this is how the graph will look like. Okay, this is the graph of y equal to cos s, a rough sketch, not a perfect graph. Okay, this graph is actually an even function. Is an even function, yes. Let's assume it's a perfect graph. Let's say I take this point from here to here, from here to here. Okay, this is negative axis, this is the positive x-axis. If we tend to close the graph, look at it very well. If we tend to close the graph along the y-axis, the graph will perfectly overlap. That is, each sides will perfectly overlap. If we tend to close it, it will actually what? Overlap the two sides. That is the idea of symmetrical about the y-axis. So even functions are functions that are symmetrical about the y-axis. All right. Okay, let us take, for example, a non-sinusoidal waveform. That is something like this. Okay, we can have this. Let's see from here. Okay, then from here again, we are taking this bottom line to be the same. Okay, let's say from let's say this is 0, this is minus 2, let's say this is minus 3. Okay, so we have 0, 2, 3. All right, so you get the point. Good. So let's assume this is a perfect graph. Okay, these two sides have the same size. If I tend to close it, all right, I tend to overlap it. It will overlap perfectly. Yes, so it will close completely the two sides. So this is it for even functions. Now, what about odd functions? Okay, for odd functions, the graph, okay, is symmetrical about the origin. That is to say, for any point on the graph, let's say minus s, okay, s comma f of x, there exists a corresponding point minus s comma minus f of x. This is it for odd functions. So why the even function is symmetrical about the y-axis, the odd function is symmetrical about the origin. This is the graph of y equal to s cubed, a sketch actually. Remember we said that s cubed is an odd function. So something like this now. Well, I've tried in this one. Wow, it looks perfect, but let's just assume so. On this graph, this is the y-axis and this is the x-axis. So for odd functions, the idea of symmetrical about the origin is this. If you rotate the graph at an angle of 180 degrees, okay, what you have at the picture initially is what you will see when the graph is rotated at that angle of 180 degrees. So this is 180 degrees. From here to here, 180 degrees. So as it is now, if I turn it at an angle of 180 degrees, what I'm seeing now is what I will see when it is turned at that angle. So that is what symmetrical about the origin is as far as odd functions is concerned. Okay? So look at the graph of y equal to sine x. Remember we said that sine x is also an odd function. Okay, let me draw a small sketch here. Let's take it this way. Let's just accept it. All right, this is the graph of what? Y equal to sine x. If I rotate this graph at an angle of 180 degrees, what I'm seeing now is what I will see. The same picture here is the same picture I will see when this graph is rotated at an angle of 180 degrees. So even functions are symmetrical about the y-axis. Okay, odd functions are symmetrical about the what? The origin. There are some graphs that are neither even nor odd. And a very good example of a non-sinusoidal waveform that is neither even nor odd is what I have on the board. This graph does not satisfy any of these conditions. Yes, it does not. If I try to cover the graph, it will not perfectly overlap because what is here is entirely different from what is here. Yes. Even if I rotate the graph 180 degrees about the center, it is not also going to produce the same picture as what I can see now. Okay, so this graph is neither even nor odd. That is the point. So there are some graphs like that are not even and they are not odd. Some functions like that. We saw some of them, some of those algebraic functions. Okay. Product of even and odd functions. This is it. If you multiply an even function by an even function, the result is an even function. If you multiply an even function by an odd function, the result is an odd function. Take note. Even times odd times even is the same thing. Multiplication is commutative. They will produce the same results. What if you multiply an odd function by another odd function? It will produce an even function. It's just like in our normal arithmetic. When we say plus times plus equal to plus. Plus times minus equal to minus. Minus times minus equal to plus. It's similar to this idea, okay? Functions and numbers are not the same. Take note of that. Functions are different from normal numbers. Okay, so this is it for product of even and odd function. So on this note now, we can say that the product of x squared and cos 2x is actually an even function. Yes, because x squared is even, cos 2x is also even, so it will give us even. Now, the product of 2s cubed and cos s is going to be an odd function because 2s cubed is odd, cos is even. So what is odd times even is going to produce an odd function. Also, we have 4x to the fourth, 6x to the second. This is actually an even function because 4x raised to the power 4 is even. 6x raised to the power 2 is also even. So even times even is even. Also, if we have x sine x, x is an odd function. Sine x is odd as well. So odd times odd is even. This is going to be an even function. Why is it important to know whether a function is even or odd when trying to determine the Fourier series of a function? Yeah, it is actually important to know whether it is even or odd because it's actually going to save time and labor, stress. This is what I'm saying. If the function f of x is defined over the interval negative pi less than x less than pi, and this function is even, let's see what happens. The series will contain cosine terms only and possibly a naught. All right. So for an even function, b sub n is equal to 0. This must be noted. A sub n and a naught are the Fourier coefficients that we need. You see that it's going to save our time. We don't need to calculate for b sub n. Okay, we just know that it is 0. It's going to be 0. So we just need to calculate for a sub n and a naught. So a naught is 1 over pi, the integral from negative pi to pi f of x dx over that range. But this is it. Since the function is even, we can actually take half of the range and multiply it by 2. Here it is from negative pi to pi. So we can take from 0 to pi and multiply it by what? 2. So this is it. A naught is equal to 2 times 1 over pi, that's 2 over pi, times the integral from 0 to pi of f of x dx. This is it. So a sub n over the range negative pi to pi is 1 over pi times the integral from negative pi to pi f of x cos nx dx. We can do the same here. The function is even, so it is symmetrical about the y-axis. All right. We can take half of the range and multiply it by 2. That is 2 over pi, the integral from 0 to pi f of x cos nx dx. Okay, so we can work with this for a sub n. So, what will be the Fourier series of an even function? The Fourier series will be this: f of x be equal to a naught over 2 plus the summation from n equal to 1 to infinity of a sub n cos nx. Remember, b sub n is 0, so we don't need it. This is for even function. Now, from this same function again that is defined over this interval, we just considered if the function is even. What if the function is odd? If f of x is odd, what are the Fourier coefficients that we'll actually need to calculate for? Some of them will be equal to 0. First of all, the series of an odd function will contain sine terms only. For even function, we had cosine terms, okay, and a naught. But for an odd function, it's just going to be sine terms. Also, the Fourier coefficient a naught is 0, and the Fourier coefficient a sub n is also what? 0. So we only need b sub n. That is the point. So what is b sub n? Let me place it here. B sub n is generally over this range 1 over pi times the integral from negative pi to pi of f of x sine nx dx. Now look at this. We are saying that the function f of x is odd, if it is odd, okay? So odd times odd is even, all right? Sine x is odd, f of x is odd in this case. So odd function times another odd function will produce an even function. And we said that for an even function, the graph is symmetrical along or about the y-axis. So what it means is that we can take half of the range, just like we did here, from 0 to pi, okay? 2 times 1 over pi, which is 2 over pi, times the integral from 0 to pi of f of x sine nx dx. So this is b sub n for an odd function. Take note. Now, what will be the Fourier series for an odd function? Is this: f of x will be equal to a naught is 0, a sub n is 0. So we'll be needing the summation from n equal to 1 to infinity of b sub n sine nx. That is it. What if the function is neither even nor odd? Unfortunately, well, we are going to calculate for b sub n, a naught, and a sub n. The 3 Fourier coefficients will be calculated for, because the function is neither even nor odd. Maybe along the line, one of them or thereabouts becomes 0. Depends. But as it stands, for even function, this is what we have. For an odd function, this is what we have as well. And for a function that is neither even nor odd, we'll have to calculate for the 3 Fourier coefficients. That is it for even and odd functions as far as Fourier series is concerned, okay? Thanks for watching this video. I hope you like it. I hope I have been able to convince you actually to subscribe to this channel, okay, based on what I have been doing all along. Remember to subscribe, like, and share this video to your friends and to your classmates. Very, very important, okay? I am the complex analyzer. I'll see you in the next video.